this class, we discuss with the salient features of main concepts of quadratic equations. Before going to deal with that, let us recall the definition of a polynomial. We know that f of x is equal to a0 plus a1x plus a2x square plus etc. Anx power n is a polynomial of degree n provided an is not equal to 0. If n is 1, if it is a first degree polynomial, then it is called a linear polynomial. If n is 2, then it is a quadratic polynomial. If n is 3, it is a cubic polynomial. If n is 4, then it is called a biquadratic polynomial, and so on. In general, it is a polynomial. Moreover, if we take f of x is equal to 0, then it is called a polynomial equation. Of special interest is the case to deal with quadratic equations in the present class. Therefore, if n is equal to 2, then this becomes a0 plus a1x plus a2x square is equal to 0. If a2 not equal to 0 is a quadratic equation. And more generally, this form could be taken as ax square plus bx plus c is equal to 0 if a not equal to 0. As only 3 coefficients are needed here, we name them a, b, c instead of a0, a1 and a2. To call this a quadratic equation, we need to have a not equal to 0. Otherwise, if at all a happens to be 0, it is not a quadratic equation. It can then become a linear equation. But we want to have a quadratic equation. For that purpose, a not equal to 0 must happen. The next thing we have to go through is roots of ax square plus bx plus c is equal to 0. We know the meaning and the difference between roots of an equation and the solution of an equation. Any value of x which satisfies this equation is called a root of the equation, and the set of all such roots is nothing but comprising a solution, we say. We are now interested to deal with the roots of the equation. From earlier algebra, we know that x is equal to minus b plus r minus root of b square minus 4ac by 2a gives us the formula to find the roots of the equation. Now, it is the time for us to go through the way in which it has been obtained. Let us look at ax square plus bx plus c is equal to 0 is given. Of course, with a not equal to 0. As a is not equal to 0, let us divide this entirely with a. Then what happens? X square plus b by a into x plus c by a is equal to 0. Send this c by a to that side. X square plus b by a into x is equal to minus c by a. Let us now try to view this as a perfect square. To make it a perfect square, let me add b by 2a whole square on both the sides. X square plus b by a into x plus b square by 4a square is equal to b square by 4a square minus c by a. You can easily look at this expression. This is just nothing but x plus b by 2a whole square is equal to, what is the LCM here? 4a square b square minus 4ac. And from this, x plus b by 2a is equal to plus or minus root of b square minus 4ac by 2a, and send my plus b by 2a to that side so that it becomes minus b by 2a plus or minus root of b square minus 4ac by 2a. And the formula of good olden days, which is known to so many of us, has now been obtained. x is equal to minus b plus or minus root of b squared minus 4ac by 2a. Like that, we will be able to have the roots of this equation here. The crucial part in this formula lies here. If b square minus 4ac is positive, root of b square minus 4ac is a real number. If b square minus 4ac is negative, root of b square minus 4ac is a complex number. And if b square minus 4ac is 0, then the roots will be minus b by 2a and minus b by 2a. Therefore, the life, the nature, the character of the roots of this equation are absolutely dependent on the nature of b square minus 4ac. That is why that particular number b square minus 4ac is called discriminant of the equation, or discriminant of the quadratic expression ax square plus bx plus c, because that is the deciding factor to know the nature of the roots. It is generally denoted by capital D, that is capital D is equal to b square minus 4ac, and it is called discriminant of the equation. Well, let us now study various cases of this D, in what way it does affect on the nature of the roots. Let us see. Case 1. Discriminant is greater than 0. That is b square minus 4ac is greater than 0. What happens to the fate of the roots of this equation? Observe the equation x square minus 5x plus 6 equal to 0. What is the discriminant here? B square, that is 25, minus 4ac, that is 24, is equal to 1, is greater than 0. Discriminant is greater than 0. You observe this equation. It is just nothing but x minus 2 into x minus 3 is equal to 0. That is x is equal to 2 or x is equal to 3. What is happening to the roots? These are two real roots and different roots. So we can state that if d greater than 0, roots are real and different. Case 2, d is equal to 0. Let us observe this equation x square minus 4x plus 4 is equal to 0. What is the discriminant here? D is therefore equal to b square minus 4ac is equal to 0, and here it is just nothing but x minus 2 whole square is equal to 0, that is x is equal to 2 and 2. We have observed that the roots are real and equal. The roots are real and equal in this case. D is equal to 0. Next, observe the equation x square. The case under discussion is d less than 0. X square plus x plus 1 is equal to 0. Consider this equation. What is the discriminant here? B square minus 4ac, that is minus 3, is less than 0. And everybody knows that x square plus x plus 1 is equal to 0 implies x is equal to omega and omega square. That is the complex cube roots of unity, and these of course can be minus 1 plus or minus I root 3 by 2. These are perfect complex conjugates. Therefore, if d less than 0, then the roots are not real. First point. They are complex. Second point. They are complex conjugates. That is the third point to note down. What I mean to say is, if 2 plus 3i is a root of this equation, then 2 minus 3i is also a root of this equation. A complex root occurs when and only when discriminant is less than 0. And if d is less than 0, then if d is less than 0, the complex roots, they occur as conjugate pairs, not as a single complex root. You can have no circumstances, you can observe no equation for which one root is real and one root is complex. It can never happen. If at all a complex root occurs, they occur in conjugate pairs. That is, if 2 plus 3i is a root, then 2 minus 3i is also a root. So this is minus 1 plus I root 3 by 2 is a root, implies minus 1 minus I root 3 by 2 is also a root. This is the nature when d is less than 0. Next, Case 4, D is greater than 0 and is a perfect square. Perfect square. What happens to this case? You please observe this equation. 2x square minus 5x plus 2 is equal to 0. You can factorize this. This is x minus 2 into 2x minus 1 is equal to 0. That is x is equal to 2 or 1 by 2. Observe the case here. What is D? B square, that is 25, minus 4ac. 4 into 2 into 2 is 16. 25 minus 16 is 9. It is nothing but 3 square. As and when D is a positive and is a perfect square, then the roots are rational. They occur in the form P by Q for some integers P and Q with Q not equal to 0. Therefore, this is a special case when D is positive and is a perfect square, then the roots are rational. And the last case is D greater than 0 but is not a perfect square. Not a perfect square. X square minus 4x minus 1 is equal to 0. You please observe this equation. What is discriminant? B square minus 4ac is plus 4 is equal to 20, greater than 0, but it is not a perfect square. But it is not a perfect square. What is going to happen? Observe this equation. X square minus 4x is equal to 1. X square minus 4x plus 4 is equal to 1 plus 4. I have added 4 on both the sides. This is nothing but x minus 2 whole square is equal to 5. So x minus 2 is equal to plus or minus root 5, and hence x is equal to 2 plus or minus root 5. Let us see what is happening here. One root is 2 plus root 5. An irrational number. Of course, a third. Another root is 2 minus root 5. Another irrational, which is of course the conjugate third of the previous one. So, what can we state in this case? If D is greater than 0 but is not a perfect square, then the roots are irrational. The roots are conjugate thirds also you can say. So, with this observation, you can state one more thing also. If 2 plus root 3 is a root of a quadratic equation, 2 minus root 3 is also a root. If 3 plus root 7 is a root of the quadratic equation, then 3 minus root 7 is also a root. Like that. Well, by summarizing all these three, let us have a tabular form type explanation or conclusion about the nature of the roots. Let us now have a summary of nature of the roots which depend on the discriminant. Let the discriminant be capital D, B square minus 4ac. For this discriminant D, we have three cases. Case 1, D greater than 0. Case 2, D is equal to 0. Case 3, D less than 0. D less than 0. If D is greater than 0, there is discriminant is greater than 0, roots are real and different. Roots are real and different, provided A, B, C are real. Provided in the equation ax square plus bx plus c is equal to 0, A, B, C must be real numbers. Moreover, in this case, we have two separate cases again. What are these separate cases? D is a perfect square. D is a perfect square. And D is not a perfect square. If D is greater than 0 and D is a perfect square, then roots are rational. Roots are rational. Moreover, here is also one more point to be kept in mind. ABC must be rational. If ABC are rational, then the roots are rational here. Here, in this case, roots are irrational. More than that, conjugate surds. Conjugate surds. This is the full picture of this case if D is equal to 0. If D greater than 0. If D is equal to 0, then the roots are real and equal. Real and equal. Of course, the two roots are minus b by 2a and minus b by 2a. And if D less than 0, roots are not real. Roots are not real. Roots are imaginary. Roots are complex numbers. Roots are not real. All these three things mean in the same way. Beyond all those things, we write roots are complex conjugate numbers. Roots are conjugate complex numbers. Conjugate complex numbers. This is the picture which illustrates the effect of D, the nature of D on the nature of the roots. Well, now let us observe some function of the roots. That is what happens when the two roots of an equation are added, multiplied, subtracted, like that. So we are now discussing about functions of roots. If alpha is equal to minus b plus root of b square minus 4ac by 2a, that is minus b plus root d by 2a, and beta is equal to minus b minus root d by 2a, one can easily see that sum of the roots alpha plus beta is, add these two, root d and root d will be cancelled. Minus b minus 2b by 2a is nothing but minus b by a. Alpha beta, what is alpha beta? Product, minus b plus root d into minus b minus root d. What happens? B square minus d square, isn't it? B square minus d square, that is b square minus 4ac by 2a into 2a, 4a square. B square and b square go away. 4ac by 4a square is just nothing but c by a. Alpha plus beta is minus b by a, alpha beta is c by a, and difference of the roots. What is the difference of the roots? You just subtract from this. Minus b go away. Root d minus of minus root d is 2 root d. 2 root d by 2a is root d by a. Of course, mod a. Why should we take that? Because we require the difference only, just the difference. So, mod alpha minus beta is root d by mod a. This is a very simple calculation and imagination of alpha plus beta, alpha beta, and mod alpha minus beta. Some more concepts regarding alpha beta we learn. Here, alpha plus beta is minus b by a. Let us have what 1 by alpha plus 1 by beta is. What is 1 by alpha plus 1 by beta? Alpha plus beta by alpha beta. Alpha plus beta is minus b by a. By alpha beta is c by a. Thereby you will be having minus b by c. So, observe the similarity here. Numerator is same. A is replaced by c. One more thing. Alpha square plus beta square. How can it be found? It is just nothing but alpha plus beta whole square minus 2 alpha beta is nothing but b square by a square minus 2c by a. It is therefore equal to b square minus 2ac by a square. It is alpha square plus beta square, and you can imagine 1 by alpha square plus 1 by beta square as b square minus 2ac by c square. Here also numerator is same, but in the denominator a is being replaced by c. One more thing, alpha cube plus beta cube. How can you get this? This is nothing but alpha plus beta whole cube minus 3 alpha beta into alpha plus beta from earlier algebra, from the earlier identities. Well, alpha plus beta whole cube minus 3 alpha beta into alpha plus beta. What is alpha plus beta? Minus b by a whole cube minus 3c by a into minus b by a. Of course, the LCM is a cube minus b cube plus 3abc. Altogether, alpha cube plus beta cube is 3abc minus b cube by a cube. You can trace the value here also. 1 by alpha cube plus 1 by beta cube is therefore equal to, come on, 3abc minus b cube by the similar way of thinking. A is being replaced by C. A is being replaced by C. A is being replaced by C. Not only that, you can have alpha power 4 plus beta power 4 also. Yes, how can we get this? Alpha power 4 plus beta power 4 is equal to alpha square plus beta square whole square minus 2 alpha square beta square. So, it's nothing but b square minus 2ac whole square by a power 4 minus 2c square by a square. That is b square minus 2ac whole square minus 2a square c square by a power 4. What is the fate of 1 by alpha power 4 plus 1 by beta power 4? You can be in a position to say on this part. Come on, what is the answer? B square minus 2ac whole square minus 2a square c square by c power 4. Like that, it is a very easy matter to look at all such things in which the functions of the roots of a quadratic equation is occurring. Yes. Next, let us turn our head towards the next topic. Let us now observe very simple problems regarding the roots and functions of the roots. First problem, if 2 plus root 3 is a root of ax square plus bx plus c is equal to 0, then a plus b plus c is equal to. Some options will be given. Let us first observe the way of making an attack on the question. What is the thing to be observed here is 2 plus root 3 is a root, let it be alpha. Automatically the other root is 2 minus root 3. Add them. Alpha plus beta is 4 and alpha beta is 2 plus root 3 into 2 minus root 3. What is that? 2 plus root 3 into 2 minus root 3. 4 minus 3 is 1. Thinking these two, we have the equation to be x square minus 4x plus 1 is equal to 0. Compare them. A is equal to 1, b is equal to minus 4, c is equal to 1. Add all of them. A plus b plus c is equal to 1 plus 1, 2, 2 minus 4 is minus 2. What is the value of a plus b plus c? It is minus 2. Well, how are we able to know the value of a plus b plus c? We could have known alpha and beta. Alpha plus beta is known, alpha beta is known. So, by knowing the sum and product, we could trace the equation x square minus 4x plus 1 is equal to 0. How? How is it possible? See, ax square plus bx plus c can be written as a into x square plus bx by a plus c by a. It is again written as x square minus alpha plus beta into x plus alpha beta. It is just nothing but a into x minus alpha into x minus beta. You observe this pattern. A into x minus alpha into x minus beta, isn't it? Therefore, if you want to have the equation, put it is equal to 0. As a is not equal to 0, a can be thrown outside, so that the equation with the roots can be given as x square minus x into alpha plus beta plus alpha beta is equal to 0. You can trace it very easily. That is, in the place of alpha plus beta we have taken 4. In the place of alpha beta we have taken 1. So with this help of this problem, we could have recollected the formula of finding a quadratic equation when the roots are given. If roots alpha and beta are there, sum of the roots is alpha plus beta, product of the roots is alpha beta, and the equation is x square minus x into alpha plus beta is equal to 0. Now we deal with some special quadratic equations which we come across more frequently. They are, observe the equation x square plus x plus 1 is equal to 0. We could have observed this equation already in the complex number system while calculating the cube roots of unity. And we know that x is equal to omega and x is equal to omega square are the complex roots of unity here. Let us recollect what do you mean by cube roots of unity. X cube is equal to 1, x cube minus 1 cube is equal to 0, that is x minus 1 into x square plus x plus 1 is equal to 0, that is x is equal to 1, or x is equal to minus b plus or minus root of b square minus 4 is minus 3 by 2a is 2, minus 1 plus or minus I root 3 by 2. Here is one root is minus 1 plus I root 3 by 2. It is denoted as omega, and the other root is omega square minus 1 minus I root 3 by 2. These are very famous complex cube roots of unity. In the chapter complex numbers, we could have come across so many times those two roots, omega and omega square. Moreover, here of special interest is the case to use the properties of omega, that is omega cube is equal to 1, omega power 6 is equal to 1, omega power 9 is equal to 1. In general, omega power 3n is equal to 1 for any integer n. Just like that, omega power 3n plus 1 is equal to omega power 3n plus 2 is equal to omega square, and omega plus omega square is sum of the roots is minus 1, or 1 plus omega square is equal to 0. So this is the special item that can be used, recalled and used in the case of this equation. Let us have one problem related to this one. If alpha comma beta are the roots of x square plus x plus 1 is equal to 0, then alpha power 105 plus beta power 105 is equal to, first option 1, second option 0, third option minus 1, fourth option none. As and when you look at the equation x square plus x plus 1 is equal to 0, on this part itself you will be in a position to recall that the roots are omega and omega square. So you write alpha is equal to omega and beta is equal to omega square. What is alpha power 105? This is omega power 105. 105 is divisible by 3. So it is a multiple of 3. Hence the answer is 1. Similarly, beta is omega square. So beta power 105. What is beta power 105? Omega square power 105. This is omega power 105 whole square. This is again 1 square is 1. 1 plus 1. What is the answer? 2. Not available. So what is the right option? On this part itself, immediately we will be able to have the answer justly by knowing that the roots of this equation are omega and omega square, that is the complex cube roots of unity. Just like this, there is one more equation. Let us now look at that. X square minus x plus 1 is equal to 0. Here the roots are minus omega and minus omega square. Accordingly, as in the case of the previous problem, we will be able to make use of the nature of omega, omega power 3n, omega power 3n plus 1, all the integral parts of omega, we will be able to use to estimate the required in such problems. The only thing that must be grasped here is the roots of x square minus x plus 1 is equal to 0 are minus omega and minus omega square. That's all. Another special equation comes to you. 3x square plus 2x minus 5 is equal to 0. X square minus 5x plus 4 is equal to 0. 4x square minus 7x plus 3 is equal to 0. 5x square minus 3x minus 2 is equal to 0. 2x square plus x minus 3 is equal to 0, etc. What concept you are able to observe in all these equations? A plus b plus c, 0. A plus b plus c, 0. A plus b plus c, 0. A plus b plus c, 0, etc. In such a case, you can say immediately that roots of this are 1 comma minus 5 by 3. Here 1 comma 4 by 1. Here 1 comma 3 by 4. Here 1 comma minus 2 by 5. Here 1 comma minus 3 by 2. Those are the roots. Yes, it's very simple to observe. Suppose ax square plus bx plus c is equal to 0 is the equation given, and a plus b plus c is equal to 0 is observed. Then what can you say? You see, if you put x is equal to 1, what is going to happen? A plus b plus c is equal to 0, and it is there in the given condition. So you can immediately say that 1 is the root of this equation. Okay, 1 is a root of the equation. What is the second root? We don't know. Let it be beta. This is alpha, other thing is beta. First into second, that is the product of the roots is, what is that? C by A. 1 into beta is beta. Beta is C by A. What can you say? The other root is C by A. A plus b plus c is equal to 0 implies roots are 1 comma c by A. It's not a big theorem. After all, a very simple concept to observe. By mere observation, we will be able to decide that the roots are 1 and c by A. Of course, we must be able to see. That is why here the roots are 1 and minus 5 by 3. Here the roots are 1 and 4 by 1. 1 and 3 by 4, 1 and minus 2 by 5, 1 and minus 3 by 2. Like that, you can be in a position to say the roots immediately. One more. Observe the equation 3x square plus 5x plus 2 is equal to 0. First plus last is equal to middle. That is a plus c is equal to b. One more. X square plus 3x plus 2 is equal to 0. 1 plus 2 is equal to 3. Another 2x square plus 5x plus 3 is equal to 0. First plus last is equal to middle. That is a plus c is equal to b. 3x square 7x plus 4 is equal to 0. Again the same concept is being observed here. In this case the roots are minus 1 and minus 2 by 3. Here minus 1 and minus 2. Here minus 1 and minus 3 by 2. Minus 1 and minus 4 by 3. What is the concept here? If a plus c is equal to b, then roots of ax square plus bx plus c is equal to 0 are. Let us prepare. Let us construct. It is given that a plus c is equal to b. That is a minus b plus c is equal to 0. A minus b plus c is equal to 0. We can understand that minus 1 is a root. Take x equal to minus 1. A minus b plus c is equal to 0. The condition is given. So, surely one root is minus 1. What is the other root? As in the previous case, let us say the other root is beta. Minus 1 into beta is c by a. So, beta is minus c by a. Minus 1 comma minus c by a. These are the roots. This is another special equation. One more thing. If b minus c into x square plus c minus a into x plus a minus b is equal to 0 has equal roots. Then A, B, C form. First option, an AP, a GP, a HP, an AGP. Direct application under the simple application of the previous concept. You observe the sum of the coefficients here. B minus C plus C minus C plus A minus B, surely 0. So what can you say? The roots are, one root is 1 and the other root is C by A, that is A minus B by B minus C. But in the question from data we notice that these two are equal. So what you say? A minus B is equal to B minus C. So successive differences are same, hence these form an AP. If you want to still proceed, you can easily have that to B is equal to A plus C or B is equal to A plus C by 2. This is the direct application of the previous concept. Yes, like this, let us now observe some more equations. Now we deal with one of most important concepts, namely common roots of a quadratic equation. Let us first observe the two equations, x square minus 5x plus 6 equal to 0 and x square minus 8x plus 12 is equal to 0. By means of just factorization, you can be in a position to say that x is equal to 2 is a common root, x minus 2 into x minus 3 is equal to 0 and this is x minus 2 into x minus 6 equal to 0. Thereby you can easily notice, just notice on this part itself that x is equal to 2 is a common root of the two equations, because all the coefficients are known here. If they are not known, we must be able to have a mechanism. We must know a formula. What is that formula? How can we derive that? Let us observe. Let the two equations being a1x square plus b1x plus c1 is equal to 0 and a2x square plus b2x plus c2 is equal to 0 be the two equations. Let these two have a common root, say alpha. Then what happens? A1 alpha square plus B1 alpha plus C1 is equal to 0 and A2 alpha square plus B2 alpha plus C2 is equal to 0 because alpha is a common root. It satisfies both the equations. So these two conditions we must have. Well, let us now try to eliminate alpha between these two equations by using just cross multiplication method, which is very familiar to all of us, that is B1 C1 A1 B1 B2 C2 A2 B2. Come on, alpha square by B1 C2 minus B2 C1 B1 C2 minus B2 C1 is equal to alpha by C1 A2 minus C2 A1 is equal to 1 by A1 B2 minus A2 B1. But alpha square is therefore B1 C2 minus B2 C1 by A1 B2 minus A2 B1 and alpha is equal to C1 A2 minus C2 A1 by A1 B2 minus A2 B1. Let us eliminate alpha between these two. So this is equal to this whole square, B1 C2 minus B2 C1 by A1 B2 minus A2 B1 is equal to C1 A2 minus C2 A1 by A1 B2 minus A2 B1 whole square. So that we can cancel one A1 B2 minus A2 B1 on both the sides because it's not equal. These are two different equations. They do not coincide. Therefore, A1 B2 minus A2 B1 is not equal to 0. We can cancel it. By cancelling that, what do you have here? This is C1 A2 minus C2 A1 whole square is equal to B1 C2 minus B2 C1 into A1 B2 minus A2 B1. If you want it to remember it, if you want it to write it, if you want it to practice that, it will be so lengthy, C1A2 minus C2A1 whole square is equal to A1B2 minus A2B1 into B1C2 minus B2C1. It's not so easy. In order to recollect that, let us now develop a new mechanism, a simple mechanism. What is that? As and when the two equations are given, you frame, you construct three determinants. First one, A1, B1, A2, B2. Second one, B1, C2, B2, C2. B1, C1, B2, C2. And A1, C1, A2, C2. The last determinant is somewhat you have to move a distance like this. But these two are adjacent. So, determinant formed by distant columns is A1C2 minus A2C1. A1C2 minus A2C1 whole square is equal to product of adjacent determinants. This is determinant, this is another. A1B2 minus A2B1. A1B2 minus A2B1 into B1C2 minus B2C1. That's all. If you want to have a symbolism type, you can name them. This is delta 1, this is delta 2, that is delta 3. Delta 3 square is equal to delta 1 into delta 2. First determinant, second determinant, third determinant, like that. So delta 3 square is equal to delta 1 into delta 2. A very easy way to remember, to write, to recollect, to practice. Yes, this is the condition for two equations to possess a common root. If ax square plus bx plus c is equal to 0 and bx square plus cx plus a is equal to 0 have a common root, then first option a plus b plus c is equal to 0. Second option a cube plus b cube plus c cube is equal to 3abc. Third option a plus c is equal to b. Fourth option none. This is a multiple answer type. You can easily say with just a mere observation that both the first and two options are correct. A plus b plus c 0 and a cube plus b cube plus c cube is equal to 3abc. 3abc. How are we able to note it? You see, observe this condition. If a plus b plus c is 0, 1 is a root, 1 is a root, 1 is a common root. Yes. If 1 is a common root, then this can be correct. True or not? Let us observe. Multiply this equation with b. abx square plus b square x plus bc is equal to 0. Multiply it with a. abx square plus ac x plus a square is equal to 0. Subtract here. This will be cancelled. B square minus AC into x is equal to B square minus AC into x is equal to A square minus BC. Therefore, x is equal to A square minus BC by B square minus A square. This is one way of getting a common root. Rather than proceeding in this way, if x is 1, you can observe with intuition this equation and this equation both will be satisfied with x equal to 1 provided a plus b plus c is equal to 0, then it has a common root. So in that way, that first option is correct. In another way, as we could proceed in the last case, we can use this condition also. A square minus bc whole square is equal to AC minus B square into AB minus C square. By expanding this whole square, and by this transpositions of the terms you can be able to have a cube plus b cube plus c cube is equal to 3abc, or a plus b plus c is equal to 0. You can easily get it. A plus b plus c is equal to 0. Therefore, that is the condition. First condition and second condition both are correct. This is a multiple answer type question. If x square plus ax plus b is equal to 0 and x square plus px plus q is equal to 0 have a common root, then the common root is some options will be given. First option, q minus b by a minus p. Second option, q minus b by p minus a. Third option, b minus q by a minus p. Fourth option, none. Let us see. As the coefficient of x square is same here, just let us subtract it. What is going to happen? A minus p into x plus b minus q is equal to 0. So that a minus p into x is equal to q minus b. That is x is equal to q minus b by a minus p gives the correct answer. Q minus b by a minus p. So what is the right option? The first option is the right option. First option is the right option. This is another way of getting a common root, provided coefficient of x square in both the equations match, that is they coincide. Then you can easily get the common root without using any other formula. This is the common root.